Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 2, Lesson 3. I wanted to point out something that I think is fun in the ideal gas law. For starters here, we are still in Unit 2, and we're moving into the third chapter in Unit 2, Chapter 12. And you will remember the ideal gas law, PV equals nRT. Sometimes it looks a little bit different. Sometimes the amount of gas is not given in terms of n, the number of moles of particles. Sometimes it's given as capital N, the actual number of particles. And yes, there's usually quadrillions or quintillions or hextillions of particles. So n is likely to be a very, very, very large number. But sometimes the ideal gas law is given in terms of n. And when that is true, then we change our constant from R to what we call KB. So instead of nRT, the right side is nkBT. What is KB? And so I just thought I would point that out to you. KB allows us to change from moles of particles to the number of particles. So if I take the number of particles and divide by n sub a, Avogadro's number, 6.02 times 10 to the 23rd. I wonder what that would give me. Let's think about it. Let's say I have 36 donuts. Yum, I've got 36 donuts. How many dozen donuts is that? Well, I'm going to divide the 36 by the number in a dozen, 12, and that's going to give me the number of dozens. Well, that's like what I've done here. I've got the number of particles, and I'm going to divide by the number in my group, the number in a mole, 602 hextillion. And that's going to give me the number of moles. Now, if you forget that, just remember that it's just like taking the total number of donuts, dividing by the number in a dozen, and that gives you the number of dozens of donuts. So, and I often do that. When I have hard numbers, I do a similar problem, what I call a companion problem with easy numbers, and it helps me understand. So now I know that n is equal to n times NA. So this n is n times NA, or I could replace n with n over NA, which I already have written there. So how did I get from here? PV equals, instead of little n, I'm going to write capital N over NA, RT. And so PV equals N, whatever's in that circle, times T, KB. KB is defined as R divided by Avogadro's number. So it's R 8.314 divided by 6.02 times 10 to the 23rd. Assuming we're doing everything in our lovely MKS units. Sometimes we also say R is 0.0821. And so I just wanted to point that out as well. Is it 8.314 or 0.0821? This is when we're in MKS units, meters, kilograms, and seconds. I think in chemistry class, you might have sometimes used this, and that's when we express things in liters and atmospheres. And, liters are great units for volume, and atmospheres are great units for pressure. But in physics, we usually express our volumes in cubic meters and our pressures in pascals. Anyway, I just wanted to point that out, that sometimes the ideal gas law is going to look a little bit different, or sometimes we'll plug in different numbers. And I just wanted you to be aware of that. Okay, so we are going to talk a lot in this chapter about a cylinder full of gas. And we keep the cylinder closed on top with this thing that we call a piston. So this can move up and down, and it can squish the gas or let the gas expand. And maybe I've put some Vaseline or something along in here, so we're nice and tightly closed and we have no leaks. If we have no leaks, that means N in PV equals nRT. N is a constant because we're not adding gas, we're not letting gas leak out. And then we often draw a little stick on here on the top so I can push down or I can pull it up. And then I have my gas in here. So this is the situation that we're going to talk about a lot in this third chapter of Unit 2, Chapter 12. And we are going to add heat to the gas, and we're going to change the pressure of the gas, and we're going to change the temperature of the gas, and we're going to change the volume of the gas. And so we're going to look a lot at, PV equals nRT. But both N and R will be constant in most problems. The number of moles is constant because no gas gets in or out, and R, the ideal gas constant, is constant. But we can definitely change around P and V and T. So sometimes we write PV over T equals NR. But since this is constant, then PV over T at the beginning equals NR. And PV over T at the end equals NR. So I write 1, 1, 1, and 2, 2, 2. We use this equation a lot in this chapter as we move things around. So that's one thing to think about. Another thing to think about is the total energy of this gas. My phone's ringing. I'm going to hit pause. I'll be right back. And I'm back. So fun when the phone rings. So I was talking about PV equals nRT, P1 V1 over T1 equals P2 V2 over T2. So there's our initial state, and then something changes, and we've got our final state. Now, one thing that is not included in here is what I was going to talk about with this arrow. The gas has energy. The gas, all these little particles moving around. Each individual particle has energy, and the sum of all the particles gives us a total amount of energy. And the letter we use for that is capital U. Capital U represents the total energy of the gas. And there's U1 at the beginning, and there's U2 at the end. So it may be that the total energy of the gas at the beginning is the same as the total energy of the gas at the end, but it may be that the gas has more or less energy at the end. So what I want to think about is how could we get more energy in there? What could I do to make U2 bigger than U1? To add energy to the gas so that at the end, there's more energy. Any ideas? Brainstorming? I'm going to tell you there's two ways. Two ways to get energy in there. Now, one of them we talked about in the previous video. Remember this picture? We could add heat. And so one way of adding energy to the gas, of increasing U, of making U2 more than U1, is to add heat energy. So I could add, and I'm going to call that Q, add heat energy. That's one way. And another way I can add energy to the gas is to do work on the gas. So very important, and I'm going to talk about what each of these means. Again, But the only two ways of changing U, the total internal energy, the total energy of all the gas particles put together, the only way of changing the energy of the gas is I can either add energy, add heat energy, or I can do work on the gas. In other words, I can push this down. And remember, if work is force times distance, if I push something this way while we move that way, so I push the coffee cup in the same direction as the coffee cup moves, then I'm doing positive work. If I push the coffee cup this way while the coffee cup moves the other way, then I'm doing negative work. So if the force and the displacement are in the same direction, I'm doing positive work. If I push opposite the direction of the displacement, then I'm doing negative work. So that would be something like, we'll talk about that later. That would be, negative work, positive work, negative work. But again, we'll talk about that more later. Heat, work on the gas. And so what we say is delta U, U2 minus U1, the change in energy is equal to Q, if I added any energy, plus W, the work done on the gas. And sometimes both of these are zero, in which case delta U is zero. And sometimes one of these is zero. Maybe one's positive and one's negative. So we'll have to do a lot with this equation in this chapter. But right now, I just want to have the idea that adding heat increases the energy and doing work on the gas increases the gas's energy. All right, what do I want to talk about next? W, the work is equal to F delta Y with a minus sign in the front. The work done on the gas is minus F delta Y. So if I'm pushing here with a force F, that's F. That's a positive force that I'm exerting. It's not negative because it's pointing down. It's just that's how hard I'm pushing. And then how far this moves here. This is going to be delta Y. And if we move down, delta Y is negative. And if we move up, delta Y is positive. So let's put this together. Work is the work done on the gas. If I've got a negative sign and a positive force and going down, delta Y is negative. What's negative times positive times negative? It's positive. So this represents positive work. And that would be doing positive work on the gas. W is positive. That increases the total energy. However, if I have work equals negative F delta Y, which is negative, F is always positive. If I'm pushing down, but the gas still expands, I'm pushing down while the gas expands, then delta Y is positive because we're moving up. Negative, positive, positive is negative. So in that case, W is negative. W is negative. So the work done on the gas is negative. That really means the gas is doing work on the thing instead of the thing is doing work on the gas. And so the gas expanding would use up some of the energy that the gas has. And so W is negative. That decreases the amount of energy that the gas has. So I want you to think about those signs in those situations. Squishing the gas is going to correspond to W being positive. Expanding the gas is going to correspond to W being negative. We always think of pushing down here. The air particles are pushing down on the top. So think about those signs, please. And then Let's expand this a little bit. Here's my cylinder. Here's the pit. So this represents the piston on the top. And this has an area here. So what I want to say is there's forces. And so if I have pressure times area is equal to force. Pressure is defined as force per area, the number of newtons per square meter. So that gives me pressure area equals force. So these are all these little arrows representing forces, not representing pressure. Whatever the pressure is outside times the area is equal to F, the force exerted. So this equation, work equals negative F delta Y, I just rewrote it. Negative, instead of F, I can write PA delta Y. But what is area times delta Y? Ooh. Area times delta Y is the change in volume. Work equals negative P delta V. That's another fun equation, which again, we will use lots this chapter, but right now I'm just introducing it. All right, I have one final thing that I want to talk about. It's short. I want to talk about equation 1017 in your book, and it's that U, the total internal energy of the gas, equals 3/2 nRT. So again, if I have this little piston that's holding my gas in here, the total energy of all those particles put together, think about it. It equals 3/2, that's a constant, times n, the number of particles, which is constant because nothing's getting in or out, times r, the ideal gas constant. So all of this is a constant. So that means U is directly proportional to temperature. This is a constant. If I double the temperature, that doubles the energy. Direct proportion. So that's really important, that internal energy is directly proportional to temperature, of course, always in Kelvin. And that's equation 1017. Feel free to check it out. That's all I got for you today. I hope you have a great day. And whatever you do, don't break the laws of physics.